All right, so recap of where we were from last time. Let's see, do we have our, here's where we have our nice little, I think, summary on top. So last time we worked on, let's just make sure we got our, yeah. So last time we worked on moving to this concept of the fiber context here, where we said at the beginning of last time, we had our state a little bit being split between two different places of, we had the run loop itself, which was maintaining its own state of like where we were and what the stack was. And then we also had the fiber, which had its own state of who was waiting on the result of the fiber, and did the fiber have a result yet, or was it kind of in the process of computing? And I guess I maybe used a little bit of insider knowledge to say that having that state in two places was going to be a problem for us down the road, and that we were going to benefit from trying to collapse that all into one state. And so last time we created this thing called fiber context, and there's actually a real fiber context in ZIO. So you can go there and you can, I think it's ZIO internal fiber context, and you can see a more sophisticated, definitely more sophisticated version of this same thing. But now we have this one thing that maintains all the context that's necessary for evaluation. So any state that we need to maintain or update, anything we do now, we're really going to be able to do in this fiber context. And then the other thing we did last time is we added the error type. We said we wanted to know how our computations can fail, or whether they could fail at all, and we didn't just want to have untyped errors everywhere. And so we added this error type E, and we added primitives for it, with the two key ones being this fail that introduces the error type, and then this fold method that lets us transform the error type to a new one, and we can potentially even eliminate it entirely if these things can't fail. And so that gave us this idea of like the two sides of like introducing a new type and then eliminating the type. So that's where we were last time. I think today we'll try to do two things to build on that. Though definitely people should feel free to jump in, and there are a couple of different directions we could potentially go. But I think what I would suggest we do for today is first do a little bit more work on the error type and look at what it would mean if we have let's say, even though our exception can't fail, what happens if someone just throws a throwable somewhere? How are we going to handle that? And I think we can potentially go from there, since fortunately we got a little bit of time with the symposium, to also look at interruption and how interruption can actually be viewed as a kind of error, and maybe even building up from that to safe resource handling. So I think that's probably the direction I would suggest we go. Another thing we could potentially do is we could work on adding the environment type. That's the other type parameter we haven't added yet. But I think we may also have some questions. So maybe I'll just briefly check in on those, and we'll make sure we're kind of on the same page from the prior sessions, and then we can dive in.
I think we're good to post in the chat.
Okay. Oh, okay, perfect. I just see the little red thing, so I'm like, all right. Well then, yeah, unless there are any objections, we will work on the error type here. So probably the biggest argument I see against having this error type at all is this idea that, well, anything can fail on a JVM for any reason, right? You could be doing anything you want and it could throw a stack overflow. So you're just kind of pretending and fooling yourself if you have this typed error that you say is a string or is a domain error or is nothing, because we could always throw any error we want. And at one level that has some truth to it, of like, we could throw any error we want, but that doesn't mean that like giving up on having types is like a good idea. And so I think the more principal way we can do this is we can introduce another channel to cover that possibility of expected failures. And so in ZIO, that's called the die channel. And so if we think about our mental model of a ZIO as this function from R to either EA, when we introduce the die channel, we're saying, well, really, it's maybe a function from R to either like a cause of EA. And so this is going to push us to introduce this cause data type that eventually we may grow it to incorporate more things. But initially, we could think of it as really being just one of two things. It's either a typed error E, or it's just a arbitrary throwable that just gets thrown somewhere in, I do a ZIO dot succeed, but then I just do throw new. That's funny, that auto-completed that, but I could just, in any computation, I could just throw an exception. And this is going to be a ZIO with, let's say, nothing for the error type, or we can pick any value we want, but this is still going to type check, even though this thing is going to throw an exception. And so we do have to have some way of handling it. We don't have to just give up types altogether to handle it, but we do have to have some way of handling it. So the way I'm going to start approaching this is I'm going to implement this cause type. And I'm going to use that to essentially say, okay, I don't have to just fail with an E. I could either fail with an E, or we'll probably just copy the terminology from ZIO and we'll say I could die with a throwable. And then I'll push that through to all the places where I'm using that E. And then I should be essentially back at the same point of nicely having everything compiling. And then once we've done that, we can maybe use this as an opportunity to talk a little bit about, okay, we have these two things. What do they mean, and when do we want to use each of them? So I think the first thing I'm going to do here is I'm just going to go to the bottom here. And so I'm going to create this new sealed trait, cause of E. And then I give myself object cause. Oh, I have that C. So now I'm saying this cause can be one of two things. It can either be a fail with an E, and so this one is identical to what we had before, other than I've just wrapped it in this new data type. But it can also be this die cause that has a throwable. And so now with this, I can start replacing some of the things I was already doing, where I was using just an E with this cause of E. And one of the things I can do with that to make my life a little bit nicer is I won't actually rewrite most of the existing operators I have. I'm just going to give myself some new variants that are actually even more powerful. And then I can just re-implement the previous ones in terms of them. So we'll have a little more work to do with the run loop, which we'll come back to in a second. But really, we have these two basic operators of this fail and the fold ZIO that were those two fundamental introducing the error and eliminating the error operators. And before, they just worked on an E, but now I have this cause of E. So what I need to do is I just need to create more essentially advanced or powerful versions of them that are just going to work with this cause thing. So I'll create this other fail cause. And this will take a cause that's a cause of E. And it's going to give me a ZIO E nothing. Oh, thank you. And this is now going to be my new primitive, because this is like the most basic and powerful one. So what I can do with fail here is this will be pretty easy if I can just re-implement this as fail cause.fail E. And then I'll need to re-implement this, go down to fail here. And so this is now going to take a cos of E. And so now if I try compiling that. Okay, so somewhat surprisingly, that all works, which indicates I'm not using a lot of types in the run loop. So I need to come back and watch that because we just did a refactoring and we haven't changed how we're interpreting that yet. But first, let's do everything other than the run loop, and then we'll kind of come back to the run loop. So the other operator we need to change is this fold ZIO one. And we're going to follow basically the same strategy. And I think this is also maybe another like nice pattern to think about is like, if you do need more power in something you're implementing, can you do it in a way that you can then implement something else in terms of that, so you're not kind of adding more elements to what you have here. And so this is going to be the new primitive. And then this one will just need a little helper here. And I think Kit is doing it right now, where we're just going to, so the non-cause variant is just going to say if it's a fail, it's going to recover from it. And if it's a die, then it's just going to essentially refail with that same thing. So this one, which I'm going to call fold ZIO cause, or I guess I'll call it fold cause ZIO, I think is our nomenclature. This one is going to be able to recover from any cause, whether it's a die or a throwable. And this one is only going to be able to recover from the fail. It's not going to recover from the die. So I think we got that thanks to, oops, we're
Almost.
Oh, I think we need to go down to our fold case here, and we need to update that as well. And so this one, just like we changed the fail constructor to take a cause, we'll take this one, take a cause. And let's see what else we got. I think we're slightly off here. We have too many arguments.
Oh, I don't think I need self.
Oh, we don't need the self because we're just calling this one. Yeah.
Yeah.
Okay. And then I think this just needs to be ZIO.failCause. Oh, I think this, this can actually, I think, just be.
Oh, what I was doing before.
We need to match on it to get the information, but it's a type nothing. Yeah.
ZIO.fail cause die throwable.
Yeah. So it's important here that this cause.die is a cause of nothing, because that means that we don't have to transform it when we transform the error type, and we still are sound here. Okay. So now we're ready to go to the run loop here. And I think we'll find one more thing helpful for ourselves, because in a couple places here, we were using this either EA type. Because we were saying, okay, we have this result and it's either an error or a value. And what the simplest thing we want to do is we just need to change the E to be a cause of E. So it'd be an either cause of E or A. But that's like a little bit of a nested data type. And we're going to use enough. I think it'll be helpful for us to introduce one more data type. And it'll give us this is like our chance to introduce all our old friends from ZIO. So I'm going to introduce another one that's I'm going to call exit. And this is, it's going to be completely isomorphic to the either E cause of A. But it's just going to give us a little bit of a more domain specific name for it, and just let us kind of be a little more clear about what's going on. as well as if we want to, we can like add some methods to it later. And this will be a
Oh, yes.
cause. Okay, so now we just got this little exit thing we can use. So now scroll up. And so this is where, when we're in the run loop, things are a little bit trickier because we don't have as much type safety. So we can't just use our kind of fixed compilation errors until it works trick. But let's try to see what we're doing here. So I think, and actually maybe we can make this a little bit nicer for ourselves. Let's take a look at this. Oh, okay, so wait, why is this? Oh, I see. Okay, so this complete thing, so we should change complete from taking an either EA to taking an exit EA. And similarly here, we've got these callbacks that we're taking an either EA. We'll change them to take an exit EA. Because we got to make all these types big enough to like encompass all the different types of results we can get. And since here now we can get this cause failure as well, we need to just make things big enough to include that. And now it looks like I've triggered some nice compilation errors for myself. So let's start
There's
following
another one down
those.
here I changed. So,
Oh, perfect. Okay, let me get to the latest set of compilation errors.
oh, another one down here looks like.
Yeah, I think most of these, like here I had a left. So I'm just going to change that to an exit.failure. I think most of them are just like this. This was a right, so this will be an exit.success.
But maybe for exit.failure, then we also need it to be a cause.
Let's see. Yes, where were we?
Failure, that was line 159. Yep.
Yep, so that can be exit.failure, cause.fail. And if we wanted to, we could make a little helper method. We could, like in ZIO, there's like exit.fail that just does exit.failure, cause.fail, and it just does those two things for you in one. It's amazing how nice having little compositional things like that can be. Meanwhile, let's see, exit dot, oh, I think I called it success. Okay. All right, and here, so I had the ZIO from either that I was using. So let me make myself a little helper for ZIO from exit. And in ZIO, we call this done. So done EA takes an exit. That's an exit EA and gives a ZIO EA. And all I can do is I match on success. And if it's a success, then I succeed with it. And otherwise I fail with it. So now I should be able to go up there where I had that ZIO from either. And I'll make that ZIO done. Okay. Let's check our compilation errors. Oops, that's not help us. Fail. Okay. Okay. So we're back to compiling. And so I think, so I think this is the other place we're going to want to push through this change here. So an unsafe run sync, this should give us an exit. And then this can be fold cause ZIO. And then if we get an E, we'll succeed with
I actually did add the helper, so we could just do exit.lowercase fail.
Perfect. Yay.
And exit.succeed.
Yay. Oh, do we have the succeed or not yet?
Oh, I added that right now. Succeed A. Yay. Tell you. A.
Yeah. Okay, let's see. And then this is going to be as instance of exit. Okay. And then,
okay, now it exists. Good, good.
okay. So I think let's see. Oh, well, so this now is actually a cause. So I think this can just be, I don't know if we have die, but this can be like exit dot failure
Cause, yeah.
cause, yeah.
Cool.
Okay. So now with a little bit of the caveat that we aren't as typed in the run loop as we are in most code. I think we have everything compiling and working again. So I think our first step could be just running a couple of our cases from last time before and just making sure this works. So let me try running like this error handling one, which I guess is 1. Okay, so here we failed, then this never got printed because we had failed here. And then we caught and we said recovered from an error. And we said the result was success. So it looks like that's still working. I think that's the main one we had that actually interacted with error handling. So I think at least we'll live a little bit dangerously and proceed from here. So okay, so far we've kind of introduced this error type, but for the die channel, but we haven't used it a whole lot. Like if we want to, we can manually introduce this die cause with the fail cause, and we can recover from it with that fold cause ZIO thing. But there's one more thing we need to do to like really take advantage of this, which is the whole point of like adding this feature was really we wanted to take care of like this case here. And the issue here is that right now this exception is going to get thrown in the main run loop. So like here, this is happening in ZIO succeed. And so where this is actually going to show up is we're going to be interpreting the ZIO succeed. And we did this thing to suspend it so that it would be in the run loop. But then we are going to call it right here. And we're just going to throw this exception and we're going to blow up. And that's not great because if we just blow up completely in the run loop, like means we have no way of recovering it from it. So like right now our fold cause ZIO thing is not actually going to work if we throw an exception that way, because we're going to throw and we're just never going to keep executing the run loop. And it's also not great because depending on what's going on, we might be running this on a different fiber and it might not even be like printed somewhere we would see it, or if not printed, but it might not be, we don't see it just if it's thrown. So we need to do a little more to handle this, but like fortunately now we've got the tools. And so a really easy way to do this is we can just basically just put a try catch around the entire run loop. And so we'll just say, as we're executing the whole run loop, if an error ever gets thrown, we're going to catch it. And what we'll basically do is we'll just set the current ZIO equal to that error. And we'll just use essentially our same error logic of we'll kind of keep going through the error handlers until we find one that can deal with it. So let's try that here. So we'll give ourselves a try. And then I gotta just find the while loop. And there, I think this one is the, let's see, try is, I feel like we're missing one.
I think that's all right. It's all match. It's just that we don't have a around our while.
We don't
loop.
have a brackets after the while loop. Yeah, okay.
So maybe we want to add that.
Try. And so we're gonna catch. And we'll say if we've got a throwable, then we'll say current ZIO is equal to ZIO dot. Right now I'm going to do fail cause dot die. We could, if we're really doing ZIO, we could just do ZIO dot die. We'll roll this for now. So we're just going to set the current ZIO equal to that. And then we'll continue with the run loop. And so what's going to happen here is we'll say, okay, we're going to set it equal to this. And then we'll just come back here to the top of the run loop. We'll go down to a failure case, because now it'll be a fail. And then we'll look for an error handler. And we'll keep going through for the error handlers. And if we either don't find any error handlers, then we're just going to return an exit with a cause.die at the end. If we find a error handler that's just like a fold ZIO that doesn't handle the cause, then we're just going to refail with that. And so we'll just keep going and we'll find the next error handler, or we'll eventually get to the end. Or we're going to find something that can actually recover from that die error and do something with it. So let's play with this a little bit.
Oops, yeah, I just added die, but I added it to the trait, so I'm
I have never been known to do that on these videos.
So it's in the right place now. So now we have die. Cool.
Okay. Okay, so let's try starting with a really simple one here. Well, so you're gonna do that, but let's do this just ZIO.succeed, throw new, no such element exception. Okay, and let's see what that looks like. Is 2.
Yeah.
Okay, so the result was failure, die, no such element exception. So even though we did something here that was supposed to be like this illegal thing we weren't supposed to do, we managed to handle it and deal with it in a principled way here. And let's now try adding on a little bit to this. So we could do something like, okay, we've got this. Let's try first doing an error handler that's not going to cover it. So this thing shouldn't run at all, because this is going to be a die failure, and catch-all only handles typed errors. It only handles the things in the E channel. And then I don't think we have all the variants for ourselves yet. So let's use this fold cause ZIO yet. And let's say if it's a cause, then we'll and then why don't we succeed with a code of 1 there. So we'll just pretend this is like a little exit code for ourselves. And if this is successful, then we'll just succeed with 0, kind of like a no error exit code. And I'll give myself a little comma there. Okay, so I think we're ready for this one. Whoa, this is what happens when I, especially when the screen is big, when Kit works on the the other part of the screen. So we did not print this, which is good. We recovered from a cause. Now, I don't, is there an issue with your printing, or we should have, I think, gotten a.
I think it might be with the root move, actually. I didn't change. I only added the silliness.
Oh, okay. All right. So maybe we should take a look at that. Let's just first give ourselves. So this by the end should be nothing int.
I think the types are correct. Yeah.
Okay. Oh, now it seems to be working.
Okay. Oh yeah. Because interesting. Because that's odd. Weird. And if we did like a map of +10, that's not going to blow up. Let's try that.
Oh, huh. No. What were you doing? All right. Yeah, we may have an issue.
Oh, I think with the other, you ran the wrong one. I think it was error handling 2.
Oh, that is highly likely. That is exactly the kind of thing I would do. Yes, okay, success 11. Let's just run it a couple more times. Success 11.
There we go.
Run the correct program. Yes, we should submit a bug report that ZIO needs to identify the program you intended to run and run that one instead. Okay, so it seems like this is working really nicely. Our normal error handling isn't recovering from these die exceptions, and our special die error handling is recovering from them. And so this is really, really nice, and I think a lot better of a solution than the kind of the JVM can throw error for any reason, so let's just like give up on types, because it lets us decide when we want to handle these two different types of errors. So if we go back here to this cause.fail and cause.die, there's a little bit of subjectivity here, but I think we've used these a good amount in the ZIO community, and I think we've developed some good, I guess what you call community standards around them, where this fail you could think of as the expected errors. You might also think about this as errors you would potentially want to recover from. And then this you could think of as unexpected errors, or errors you can't recover from in a sensible way, partly because you didn't expect them to occur. And so like I mean, if you are the red ZIO kind of, you've heard different things I said, like I think I've used this analogy before of, if anytime you're like talking to someone and you kind of say like, what might go wrong? The reality is probably a million things can go wrong, but like the helpful answer for them to tell you of what might go wrong is like a limited number of things that might actually occur. Like if we say like, well, why might like the ZIO release get delayed? If I say, well, it might get delayed because like either, this PR isn't in, or this person doesn't fix this bug in time, then like, it's like, okay, those are like errors, right? That we could handle in some way. We could say, oh, well, does that person need help with the PR, or should someone else work on this thing? But if I say like, well, yeah, that could happen. I could also get hit by a bus. Aliens could come. Like
Singularity, yeah.
Singularity, like that's like, I mean, at some level, yeah, I guess it could, but it's kind of useless for everyone. And it's kind of the same thing with this error handling thing. And if you're like, oh, well, you have to reflect the JVM, so like you can always have a Stack Overflow, so your error can always be controllable. Like, yeah, some of that's theoretically true. That's not helpful for anyone. So this gives us the tools to really deal with that. And this way, when we really do say like we want to recover from those throwables for some reason, of maybe we're like getting ready to give the final result back to the user, and we want to say, well, whatever the result was, even if it was an unexpected failure, I still want to log it, or I still want to return a particular type of string rendering for it. I have the tools to do that, but I can choose when I want to deal with these two different types of errors. Okay, so I think that's like one additional feature added, so yay. Does anyone have any questions or anything more we want to talk about there before we keep building on this?
I think we're all good in the chat, at least.
Okay. I'm really hoping people are like getting stuff from the chat versus like just silent of like, this is all craziness.
I think
all
we're
right.
also, competing with the.
We are competing with John. Yes,
Okay.
that is true.
Fewer people, but that means if you have questions, fewer people who are here.
Seriously, this is like perfect time.
Extra important.
Okay. So I think where I'm gonna go from here is, I think now we really have the infrastructure to start dealing with interruption in a principled way. So if we go back to kind of our like set of things we had. So before all this, we had the declarative encoding, we had the stack safety, we had the concurrency, we had the custom execution context. I think even at the end of last time, we could have given ourselves a half check on the error handling, but I think now that where we are right now, we can give ourselves a full check on that. And so the last real two big things we have are interruption and the environment. And I think I'll take on interruption first, and then we can come to the environment. So for interruption, what I ultimately want to implement is I want to implement this interrupt method that, like, I think one of the things we're used to that's really cool about ZIO and really differentiates it from something like Future is that you can interrupt a ZIO computation that's ongoing. So if let's see, I don't know if I have I think we have, okay, so we don't have forever right now, but that would, I think, actually be pretty easy for us to make. So there's this forever operator that is basically just going to take this thing and then it's going to run it again and then do the same thing. So this is just basically going to run this thing forever, which sounds like it wouldn't be useful, but it's actually pretty useful a lot of the time for, like, if you want to, like, take a worker that, like, takes values from a queue or something like that. And it's also useful for examples like these to create things that are going to go forever so we can then stop them and prove that we can stop them. So we're going to create that just to, like, set ourselves up. But so what we're going to want is most basic thing is we're going to want the behavior that when we call this interrupt thing on a fiber, the fiber is going to stop going. But we're also going to want to do this in a way that is principled, where we can do something once that fiber completes, even though we're interrupting it. So we want to have the concept of a finalizer, where we say that even though I interrupted this fiber that was maybe like working with a file, I'm still going to go ahead and close that file no matter what. Because otherwise, if all we want to do was just kind of interrupt without resource safety, like, we could kind of build that in the future, but, like, that doesn't really give us the tools to build larger applications that are safe for interruption, because the odds are if we interrupt ourselves, we're going to leave ourselves in this, like, terrible state where, like, our files are half open and all this stuff is going on. So we really also need this ability to do finalizers along with interruption. So we'll tackle those two a little bit together. So the first thing we can do here is, this is an example of where the fact that we created this fiber context thing here and we put everything together in one place is going to start paying off for us. Because what we're going to do is we're going to create a new.
It's an atomic Boolean. Let's see. And okay, I see.
Yeah, and one thing we could look at is, like, do we want to make some of these things like part of the same state or leave them as different state? But right now, I'm just going to have this atomic Boolean here. And so then what I can do is, so the implementation of interrupt, which I think is somewhere, oh, I know, because I didn't want to implement it, I left the question mark here, which I shouldn't actually do, because I should leave that abstract, which is then going to require me to implement it down here. And so the really easy implementation of interrupt can just be interrupted set true. And so this is where, like, I would have had a problem with this if I had the fiber context and the run loop being separate things, because I would have been doing the interrupt in the fiber, but I'm actually want to use this fact that I'm interrupted in the run loop here.
And for that, the line 43, don't we have to wrap it in a ZIO of some sort, maybe?
Oh, that would be a very good idea. Brilliant, in fact. Okay. All right, and I think we will actually be compiling with that change. Oh. What's that? Oh, thank you. Yeah. Yeah. Okay, perfect. Yeah. Okay, good. Okay. So now what we're going to do is we're going to essentially add one more check for ourselves when we are in the run loop. And so we'll start with like a very like simple version of this, and then we'll kind of build to like a little bit more like that, what we actually need. So the easiest thing is here, I could just say, when I say val should interrupt is interrupted.get. And then, we can actually, at least initially I'm going to leave this even, yeah, we can do this. So then we can say, yeah, should interrupt, then we'll just say loop equals false, and we'll be done. Otherwise, we'll do this whole thing. Oh, shoot, hold on, I think I'm doing, no.
Oh, we're in
Yeah, yeah, I'm doing this in totally the wrong place.
Okay. We want it in the
Let's
actual loop, right? Yeah.
Yeah, exactly. I saw loop, but yeah, this is a different loop. This is for the atomic cooling update. Let me go down to where I should do this.
130, I think.
Yeah, exactly. Okay, and now I think I will give myself the brackets around the while.
I'll add it to the end.
Okay, cool. All right, so we're gonna say, we're gonna get this atomic Boolean, and we're gonna say if it's true, then in our most naive interpretation, we would just set loop to false and we would not do anything else. We would just say, oh my God, we got the interrupted signal, just like drop a bomb on the whole thing and just like don't even try to do anything else. And let's, I think maybe we're.
Try one more time. I think maybe there was
okay.
A mismatch.
Maybe we have something slightly off with our brackets here. If should interrupt, loop equals false.
I'm gonna nudge all this over to make it clear.
Yeah.
I think we need one more down here, right? Yeah. Oh, and then we need one outside of that. Okay, now it's all good.
Yep, perfect. Okay. All right. So let's try this and just see if we can create a like little example for ourselves. So let's call this interruption. Howdy. Let's see. Do we have? I don't think we have delay right now. We have sleep, or do we have one of those?
Let's see.
Maybe we never created that.
No, we never.
Oh, I guess we don't have. Oh, okay, that's fine. I think we can just do. I think we can try doing for fiber, and so print this forever and fork it, and then interrupt the fiber. And yield unit. Okay, let's see how this is looking for us. This is the number. Oh. I'll just do. Okay. Like video run. I think it's maybe interrupted even too early.
We get one howdy.
Yeah,
so
yeah, this one interrupts super fast. Like we almost
need.
need. Yeah, I mean we could just do. We'll do the
poor man's sleep.
The poor man's sleep, exactly.
Oh, I guess a different one.
Yeah. Oh, I did 7. Yeah.
Cool.
Okay. So we've got very aggressive interruption there, but that's like not the greatest in a way. Of we've got like no concept of finalizers right now, and we just kind of just completely blow up the run loop. So let's think a little bit about how we can do better there. So the first step is we want to make this interruption a value. So just like when we had the die case that we started this session with, and we said, well, okay, we have this possibility of a throwable, like how are we going to deal with this? And once we made the throwable into a value in this die thing, then it turned out to be pretty easy, because then we just had operators that deal with values, and they were basically implemented in terms of that fold cause ZIO thing, and we could fail with that, and we could recover from that, and life was actually pretty like easy for like introducing this like complexity. So what we'll do here is we'll add one more case to this, and I'm just going to call this interrupt, and it's going to extend cause of nothing. In the real version, this also has like a fiber ID, which is basically like who did the introduction, you know, who did the interruption. It's kind of like if you got murdered, like who's the person who stuck the knife in your back. But for this, I think it's fine if we just have this like object just says you're interrupted. Doesn't worry about who it's from. And so once we have this, then, so this will just mean we are being interrupted and need to execute our finalizers and then immediately terminate. So we've got this, and we just need to do something with it. And it's actually going to be somewhat similar to what we did with the what's it called, with the thrown exception. So just like here, we did the try, and if we caught it, then we just set the current ZIO equal to that die. If we're interrupted, then we just, well, I think we'll have to have slight complexity we add to this, but basically we're just going to want to set the current ZIO equal to that cause.interrupted, and then we'll kind of build in some error handlers that will have like an error handler that can handle that interruption and do something with it. And that's how we're going to represent a finalizer. So to do that, so we're no longer going to want to say set loop equal to false here, but instead, so our most naive thing we could do is we could say current ZIO equals ZIO.fail cause.interrupt. Thank you. Now we have a couple of complications we got to watch out for here. So the first one is we've just got a little bit of an issue, I think, around the management of the stack here, because at this point, we've already got a current ZIO on the stack, because, or sorry, not even on the stack, but we've already got something else being the current ZIO, because we got something when we executed the continue function before. So if all we do is this, then we're overriding that next thing. And that next thing could itself be a finalizer that's supposed to handle our interruption. So I think we need to do one more step here, which is we need to do stack.push, and then this can be current ZIO, do blank. So we basically need to say this current ZIO we have, we got to push it back onto the stack. And then we got to replace this one here with this ZIO.fail cause. We could probably also just do ZIO.fail cause to the next one, but I think this will work for us. And then the other thing we've got to watch out for is
Quick question.
Yeah.
And this is because in case the interrupt is handled, we then want to be able to continue executing along and not lose our place. Or even if we do interrupt and stop, like if we're actually interrupted and we stop doing anything, shouldn't we then, we don't care about the current ZIO, right? Because we're interrupted, we're never going to do anything else with it. But is this for the case where it's handled? I guess this is the question.
Well, so what I'm worried about is, and I mean, let's talk through this because this is definitely a little wrinkle, is let's say that the current ZIO is something like a fold that says whatever the error is, ZIO succeed, close the file, whatever the success is.
I didn't get that. Could you try again?
No, see.
What was that, you or what was that?
That was Siri. That was Siri. Siri does not understand how ZIO works.
So imagine that this is the next ZIO we have here. So it's a fold that says whatever the cause is and whatever the success is, we want to close this file. So if we're interrupted, then, and we just overwrite it, then we're just going to basically delete this thing. Does that make sense?
Yes. So if we're interrupted and we override this, we're just going to delete this. But so I guess my question is, I see that we're going to delete it, but if we're actually being interrupted, that's okay to delete it, right? Because we're actually supposed to die. We're supposed to be interrupted. We're not supposed to continue, right? We're interrupted. So who cares what we were doing? We're never going to get back to it. But
well, but so that's where the concept of this finalizer comes in, though.
Okay.
Because this thing here, at least right now, this is saying any cause, I want to recover from it and do this.
Okay. Oh, and yeah, any cause. This is the fold cause. Yes. Even
this is the fold cause.
Even if it is
right.
interrupted, we're going to do this. I see.
We're supposed to do this, but if we don't push this back onto the stack,
gotcha,
then we could overwrite that and we could not do that.
Okay. Yeah. So in the case that the thing that we're currently doing is something that's even supposed to recover from an interrupt, and we're interrupting that, that would be weird if it disappeared. That would be sort of like a weird race condition if you happen to interrupt thing.
That would be a weird race condition, yeah. The other thing we might do is we could potentially, I think if we might be able to push this into the continue and check for it there, and that might be easier because we would do it when we hadn't done a current ZIO yet. But I think this will be okay here.
Yep, makes sense, I think.
So then the other thing that we've got to watch out for is we don't want to just infinitely recurse here, because right now we're saying, well, if we're interrupted, then do this. Then we'll loop again. We're still interrupted, do this, loop again, and we'll just kind of stay here forever. So we're going to want a couple more variables here to help us. So let's so I'm gonna do another one of is interrupting. And so this one is someone sent us the signal to stop executing. And then this one is going to be, are we in the process of finalizing ourselves?
And this feels like something that maybe in the ideal case, we'd have a sealed trait for, right? Because there are these two states that maybe we don't care about both of them at the same time, and they're slightly overlapping. But because we want the guarantees of atomic booleans, we can't do that.
Yeah, and we're super low level here. Yeah, exactly. And so then I think what we can do for ourselves here is we can create a helper method for ourselves, and maybe this will call should interrupt. And so our logic is basically, if we're interrupted and we're not already in the process of interrupting ourselves, then we should trigger the interruption. Does that make sense?
Yeah, totally.
Okay. So then I think we can go down here. And I will say all this with a caveat that this is low level stuff. So we may do this and we may realize we messed something up and we may come back. So then here, I think we'll say, so if we should interrupt, then we need to interrupting, or is interrupting, I think is what I called it.
Oh,
We'll set.
actually,
Sorry,
so should interrupt actually, it's currently it has an or, maybe that should that be an and?
Oh, yeah, thank you. Where is that? Yes.
That's 48. But that should
Yep.
be an and.
Yeah,
right?
that's because we only want to trigger this essentially once when we're interrupted and we're not already interrupting ourselves. And as soon as we do it once, we'll set that is interrupting to true. So then that'll never hit again. And so that first time we go through, we'll do that. We'll set that. And
Let me loop.
okay, so and we'll loop. And at this point, at least as we've set it up right now, we don't have anything else that's going to recover from that interruption. So let's, so I think this should, let's check. Okay, I think we're compiling here. So let's try running this. And this is 3. And there we go. Okay. So we still managed to get the benefits there of we were able to interrupt that. But now let's try adding something else here to help ourselves out. So let's do another operator called ensuring. And so this is going to, well, we only had that because we don't have an environment yet. But so this will let us give us a new ZIO that can't fail and is just can do any side effect. And it's going to give us back a version of this. And this one is going to be ZIO dot fold cause ZIO. And we'll just say, if we had some error, then we're going to run this thing. And then we're going, oh, this is actually a cause. Oops, sorry. And then we're going to fail with that cause. And if we got an A, then we're going to, and I'll call this finalizer maybe to be a little more clear.
Nice.
Okay. So now I should, let's see, am I still compiling here? Maybe I screwed up.
Fold cause ZIO is not a member. Is it fold ZIO cause or no? It's not a member.
Oh, no. Oh, because it's a method on the trait, not the object.
Ah, yes.
That was a very silly thing. Okay, so now we should be able to add something here where we should be able to say ZIO succeed, print line howdy forever. Then we should be able to say ensuring ZIO succeed, print line. Goodbye. Nice.
The proper
Okay.
inverse.
Let's see how this works for us.
Yeah.
And look there, we got Bowdy. Yay. So this is the beginning of the concept of finalizers here. And so just with this, like we're already like, even our toy ZIO is like more advanced than Scala's future at this point in terms of ability to support interruption and resource safety. Does what we've done make sense to folks so far? Any questions?
It's kind of cool that it's all less than 400 lines too. It's all 309 lines apparently.
Yeah. And a good amount, I think we got some like just like random comments here and this and that. Yeah. Yeah, it's lean. Any other questions or comments from people?
No, happiness
Okay.
as well in the realm.
All right, awesome. So let's go from here. So the other thing that we really want to really have resource safety is we need the ability to control where we're interrupted or can't be interrupted. So we've got a very limited form of that with this like ensuring thing, because it's going to run, we saw it ran even when we were interrupted. But sometimes we need the ability to like do a set of things, and we need to make sure that while we're doing that set of like important things, we don't get interrupted. And this gets particularly important because this only is guaranteed to run if the thing that it's attached to starts executing. So if that thing never starts executing and like this ensuring never gets added to the stack, then the finalizer is never going to get run. So the other thing that we want to add is the ability to designate regions where we can be interrupted or where we aren't subject to being interrupted. So for that, we're going to follow a little bit of a similar pattern to what we did when we added the executor, where it'll be, I guess, as you say, a little bit of like maybe a 3 or 2-step process where we're going to need to add some new state to the run loop. So like when with the executor, it was an executor. With this, it's going to be this state of like, are we interruptible or not? Then we're going to need to add some new primitives to the ZIO language that we're developing here that let us get and set that. And then we're going to need to wire those up in the run loop to actually have the interpretation of those things change that variable. Does that make sense?
To me, it does. And, but, you know, it's good
that may be dangerous because you also have a very good
but also, no, I actually haven't really dealt with this much before, but I think we're following the same pattern that we have been, as you mentioned, with the executor, with some of this other stuff. It's good that it's kind of repetitive, and maybe even it's good.
Okay, so I'm gonna mess up one more of is interruptible, and so this is are we in a region where we are subject to being interrupted?
I'm guessing we have to extend this to check that we are.
Yeah, we're interruptible, exactly.
And yes, probably want this first, so it short circuits.
Yeah, I think that's good. And one nice thing about this is it's already going to give us a nice property automatically that one of the things we want is even if we're in that uninterruptible region and we get the interrupt signal, we don't want to interrupt ourselves right away, but we also don't just want to like throw away that interrupt signal. As soon as we get out of that uninterruptible region, we then want to trigger the interruption. So this is going to do that for us because every time we go through the run loop, we're going to check this thing. And so if we get interrupted while we're not interruptible, this is going to be false, and we'll keep going while we're not interruptible. But as soon as this changes, then this whole thing is going to be true, and we're going to interrupt ourselves. So that's kind of going to work pretty nicely for us, just the way we have that set up. Does that make sense?
Yeah.
Okay. So we've got this thing here. So the next thing that we need is we need some operators to change the interrupt status. And with these operators, sometimes there are like 2 different ways you can do it. You can either like kind of make the primitive one like one on a ZIO, or make the primitive one one that's just like its own, just like static thing. I think here I'll make it one that like takes a ZIO. So I think I'll maybe make it on the trait. And yeah, I'll just do it like right here. So I think maybe I'll make this something like set interrupt status. and it'll have a interrupt status that I'm gonna kind of follow Kit's thing, and interrupt status doesn't exist yet, but it will. And this is going to give me just another ZIO that has same success values, but is now has this interrupt status. And I think as Kit's doing, they're basically just going to be two. You're either interruptible or you're not. And so then, yeah, perfect. So then
Yeah,
the other thing I'm going
to
to
the bottom.
do, yep. And then this, I'm just going to use my usual pattern. I'm just going to create a new little term in my ZIO language here. So I'm going to do not shift, but I'm going to do ZIO dot set interrupt status. And then I'm going to put myself there, and I'm going to put the interrupt status there. And this isn't going to compile right now because this thing doesn't exist. But we'll go down and we'll make it exist if it doesn't, if Kit has not already added it. Okay. So
Here, I have it a few lines above.
oh, you already did add it. Okay, perfect. And I think the only thing we need is, at least the way I did it, we also had the ZIO there.
Oh yeah.
So we'll just need the EA here and here. Okay. So now that should all be compiling. And now I should have just, yeah, I'm getting some warnings because I haven't handled that in the run loop yet. And before I handle that, I'm going to give myself, I think I'll give myself one or two more operators here. So this is like the most general one, but like if you've used ZIO, like if you've done anything with interruption, you probably have not used that one. The ones you probably use, maybe, is we can just have one that's called interruptible. That's just set interrupt status dot interruptible. And then we could have another one, yeah, uninterruptible, EA, set interrupt status dot uninterruptible. So those will be like a little bit more intuitive for us. And then what have I done wrong here?
I think it was me.
Oh, hello. Okay, perfect. Nice. Wow, yeah, I didn't even know you could do that in just like normal, like non
You can put emojis anywhere.
Slack or whatever. Yeah, I just didn't realize. Okay, so this is gonna have like an easy part, I guess, and like a slightly more complex part. So there are, I guess, two relatively easy parts. So one relatively easy part is clearly after we evaluate this, we've got to like actually evaluate this ZIO inside here. So one thing we're going to need to do is we're going to say current. Oh, we don't even do that because we've got this. Oh no, we do. We need to say current ZIO is equal to ZIO. So that like definitely we need to do. And another thing that I think is pretty clear we need to do is we need to set whether we're interruptible based on this interrupt status. And what we can do there is if we go down to interrupt status, we can just make some little helper method for ourselves here.
Do Boolean.
Yep.
Nice. Oh, can Copilot do it? What is that thing?
Yeah, that'll work. Okay. So now we've got that. I can go back up to the run loop here.
I think I fixed it. There was a.
I think I just need to actually use it. Let's see, where am I? Set interrupt status. Okay. Let's see. Yeah, I think we got some other error.
I think it's good now. There was a. Yeah, we just needed to.
Oh, I think we need maybe we need
qualify.
Yeah, exactly. That's what I got for.
No.
Okay, perfect. Let's see. Yep. Okay. So we've got those two. So.
Oh, can we close the side drawer just due to?
Oh yeah, no, 100% with our giant screen. Yeah. Otherwise, it's annoying. Okay. So we got those two. So we have one more complication here. And that is that we've got to set the interrupt status back to what it originally was, because like the way this is going to work if the user writes their code is they're going to do something like ZIO1. They're going to do something like ZIO1 star arrow ZIO2 dot uninterruptible star arrow ZIO3. And so with what we've done so far, this uninterruptible is going to make this guy uninterruptible. But then like we've just set that status and we never like unset it. So it's just going to be like there for the life of the like ZIO program. So someone's going to be like very confused when they try to print howdy forever in here and they can't interrupt the printing of the howdy, as lovely as the howdy is. So what we need to do is we need to make sure that when we're done with this thing, that we set the interrupt status back to whatever it previously was. So what we could do is we could do something like we'd say val old interrupt status is equal to
oh, we might need and I'll make a from interrupt from Boolean.
perfect. Actually, I think we can get away without that, but because I think we can just call this old is interruptible, let's say.
Oh, there you go.
And then, so there are a couple of different ways we can do this. One of the trade-offs you have a little bit as we kind of implement these things is like ZIO's, even our version of ZIO is getting powerful enough that we can implement some of these things, either try to kind of do them directly in the run loop, or we can just use like the existing ZIO tools we have to do them. So like here, like one way I could do it that would be like more like low level is I could, and I think this is actually the way it's currently implemented in ZIO, is like there's a separate like interrupt status restore that's actually its own special subtype of continuation. And when you go through the continuation stack looking for something, it's like its own special thing. And you know, okay, as soon as I see this, I need to like restore the interrupt status. So that like you can definitely do. But I think here we can actually just do a simpler one. We can kind of use our existing tools and we can say this is just going to be ZIO dot ensuring ZIO dot succeed is interruptible dot set old is interruptible. Right, so we're saying this is the ZIO that we want to run in this. Okay, did I do something? Good.
Oh, yeah, something happened on the next slide. I don't know what it was.
So this ZIO here is the ZIO that I want to do, let's say uninterruptibly, because the default's kind of interruptible. So typically, at least the initial change will be to make it uninterruptibly. So this is the one I want to do uninterruptibly. So I'm going to set myself to not being interruptible. I'm going to now set myself as being, this is the one I'm going to do. And then as soon as I'm done with doing that, no matter what, even if I fail, I'm going to set the interrupt status back to what it originally was.
Nice.
So yeah, I think that'll give this to us. We may be a little bit challenged in our ability to like fully demonstrate all this stuff without having like developed like promises or refs or some other things that you use to like super deterministically test this. But I think maybe let's try something like, what if we do, let's see, I think we have repeat. So what if we do something like repeat 100,000 dot uninterruptible, and then we let's just grab this guy here and I don't know, howdy two or howdy, maybe that's more fun.
Yep.
And we'll do this forever. This won't be interruptible. And then we're going to do this whole thing in sharing bounty, and we're going to fork. Okay, and maybe let's see, maybe we should shrink this. I'm totally playing with this. We basically, ideally, we want this to be short enough that we make sure this starts, but doesn't that we hit it somewhere in here. And I guess we'll see. But okay, so let's see what this looks like. So let's do 1. I think this was 3, if I remember correctly. So lots of howdy.
Oh yeah, so definitely longer than 500 milliseconds.
Okay, and so we see that, yeah, maybe we got to play with that. But so we see this never got printed because as soon as we got out of this uninterruptible region, we checked for interruptibility, we checked for interruption here, and we determined that we had been interrupted. So then we never even executed this. But yeah, maybe we can like, I guess the fun example would be if we can show kind of getting interrupted partway through the howdy, but let's see if we can make that.
A little,
yeah. Oh, all right, so there we go. So we did all of our howdies, and I think I did so many howdies that I like, no. Okay, all right, so we got all our howdies, and then we started doing our howdies, and then we got interrupted. So we saw kind of a couple of different examples of timing of if we get interrupted here, then this never executes at all, but this still executes to completion. And if we get interrupted while this is going, then we'll just stop it wherever we're going. And so like here we saw like some howdies, but then we didn't get all the howdies because we would have got infinite howdies if we got all the howdies. And then we got the bounty no matter what, because that was in this finalizer here. So that's kind of one of the key things that we need for resource safety. And if we wanted to, the next steps from here would be we can use the existing interruptible and uninterruptible and the ensuring to implement another operator called uninterruptible mask, which is like a more complicated variant of that basically says, well, make this uninterruptible, but like give me this little region inside that is going to have the original interruption status. And then with that, we could implement the operators called bracket in ZIO1 or acquire release in ZIO2 that says, okay, let me acquire this resource, then use it and guarantee that no matter what happens, as long as I acquire the resource, I'm going to release it. But I'm also we're close to time here, and I think we've had a couple where we've probably gone over a little bit on time. So maybe this is a good time to open it up for questions, or if it'd be helpful for anyone to go back over anything or just hit on anything else, and yeah, make sure people feel good about this, because we definitely it's getting it started off maybe intermediate and it's getting more advanced.
Yeah, but I do like how it's the same pattern over and over again. And I think we mentioned at the beginning, I mean, yes, our intention is to show how ZIO works, but also to sort of show how these design techniques can be used in your own code, right? You create a language for yourself to use, and then you sort of pile all the complexity, constrain all the complexity to a run loop, basically an interpreter. And as you can see, when we need to add new features, we don't need to change everything. We just need to sort of add a couple new little handles to our language, maybe add a couple new little variables to our run loop, tweak the semantics a little bit, but everything doesn't have to change. We are able to layer on complexity. And maybe in the real world, some of these new features might step on other features' toes a little bit. You need to balance everything out. But so far, we haven't run into too much trouble, and we've implemented something pretty complicated and powerful in not too much code. So hopefully, even if you don't feel like introducing a competing functional effect library, you'll find it useful in your own libraries and DSLs and whatnot.
Yeah, and I think hopefully you can see today how that idea of moving all the state into one place really helped us here, because having it all together, it was very easy for us to introduce those different things, and then both kind of introduce the state, introduce the operators that worked with it, and have all those things fit together. And that would have been a lot harder to do if we had the state split across different places. So I think that's another thing to think about as you're implementing these. Of one of the advantages of having this declarative encoding is you get to put all that in one place, and really making sure you're taking advantage of that.
Yeah, it's not quite global mutable state. It's like local edition. Well, awesome.
Anything else here?
Jinx, I don't think there are any questions. No, I'll check the
All right.
Discord. But no, yeah, that was awesome. Thank you, Adam.
All right, perfect. Well, cool. We will see everyone next week.
Take care, everybody.
Bye.
Peace.